So we were talking about subgroups. Now if you're given a subset of a group H, then and how do we check H is a subgroup of G? So is there any simple way? So we will answer this question by a theorem, right? So this is called the one step subgroup test. So let it be okay. Let's see. So let G be a group and H be a non-empty subset of G. Okay, then what we are telling is the theorem is simple. For any AB, inside H, AB inverse in H if and only if H is a subgroup of G. So this means H is a subgroup. H is a subgroup. So we need to prove from either side. So if AB inverse in H, for any AB in H, then H is subgroup. If H is subgroup, that other way. So let's try the easier part. Okay, so suppose that H is a subgroup of G, then you take any AB in H. So being H is a subgroup, then B inverse is also in H. Okay, so this is because existence of inverse in H. Now by closure property in H, AB inverse in H, by closure property of H. So we have done that. So if H is a group, AB inverse in H for any AB in H. Now the task is assume that for any AB in H, we have AB inverse is in H. Now we have to prove that H is a subgroup. So first thing we have to we are doing it in a special order. So first we show that identity, existence of identity. So existence of identity. So how do we do that? So we know that any two numbers AB in H, we have A B inverse in H. This is we have. Now we put B is equal to A. So what happens? A inverse is in H. What is A inverse identity? Is in H. This is already in G. So here A inverse is E, which is belongs to H. So identity is proved. Okay. Now let's prove the existence of inverse. So existence of inverse. Okay, so now what we have is what we are going to do, we should always look at this fact and accordingly we put A and B, right? So now what we need is we put A is equal to, so let B is an okay, so let A be an element of G. We need to prove that A inverse exists. So in the above equation what we put is, we put A equal to E and B equal to A inverse. So any numbers A B inverse is there. So that what happens, E is there in H, we already proved it. A is already in G, so E A inverse is in H. That means A inverse is in H. So for any A in H, so I should take H, we have A inverse is in H. So in existence of inverse there. Now we have to prove the closure property. Closure property. Okay. So for closure property, what we want to do is, so uh, yeah, so let's take A in H and B in H, right? We need to prove AB in H, right? Now we already proved that inverse exists, so this means B inverse exists in H, right? Fine. Then what we want to do is, we want to take, so what is our I will denote it in a different variables. So xy is in H implies we have xy inverse is in H, right? So what here, what you have to put is, you put x equal to A and y equal to B inverse. So what happens is, we have A, B inverse, all inverse belongs to H. So what is B inverse, all inverse? The inverse of opposite is B itself. So AB is in H. So in that way we will prove that a closure property is done. So what we have proved, so associativity will be carried from the G itself. Now we proved that there is inverse, identity and closure property all is there. So what is the test? Test is, again I am going to write, if you want to check H is a subset of G, if you want to check H is a subgroup, if and only if AB inverse H, if and only if H is a subgroup of G. So that is the only thing you need to check. So we will see some problems regarding how to use this to prove that a particular type of sets are subgroups. Okay, so first thing we need to see, let's see this. So let G be an abelian group. So it is a commutative group, AB equal to BA. So let G be an abelian group. Now you consider a subset of G like this. All x's in G such that x square is equal to E. Okay, so we collect all elements where it's x square equal to E. So what we, it is actually similar as order 2 elements. Order 2 elements in G. So that is the set, right? Because we know order means what? The first time it hits a number, the exponent is E, that is the order, right? So here the first time it hits, like those numbers. So one more thing is there, order 2 elements union the number E, because for E its order is 1, right? So that is also here to say. So this is exactly all elements of order 2 and also the element E. Okay, how do you prove that this is a subgroup? So what we need to so what is the claim is, what H is a subgroup of G. So how do you prove it? So to prove it this, we use the one line subgroup test. So we take two elements AB from H. So what is the condition then? If A and B belongs to H means x square is equal to E. Similarly, B square is equal to E. Now what do you need to prove? We need to prove that AB inverse in H. So correspondingly, so what is the meaning of that? We need to prove that AB inverse square is equal to E. If we do this, we are done. So how do we do? So start from the left hand side. So AB inverse square we can written as AB inverse multiplied by AB inverse. Okay, fine. Now what you will do? So because this is an abelian group, it is so we should note that it is abelian. That means xy equal to yx. So here what I can do is I can write AB inverse equal to B inverse A. Like that you can write. This implies by associativity I can write it A square B inverse. So A square is equal to E. That's what it tells you. So this will give you B inverse times B inverse. So it is B inverse square. Okay. Now we need to know what is B inverse square, right? So for that, let's take uh, one thing, right? For example, let's take T is equal to okay. So yeah. Okay. So now let's look at what is B inverse square. So let's take T is equal to B inverse square, or we the just previous step, B time B inverse B inverse. Now multiply both side by B, then what you get is B inverse B inverse, and this is B inverse. So this is B inverse. So again you multiply left side by B, that is B square T is equal to B inverse, that is equal to E. So what you get is B square times T is equal to E. That means T is the inverse of B square, right? So let's substitute that is here. So this is B inverse square is indeed B square inverse. So what is B square? E inverse, that is E. Okay. So what we have proved is AB inverse square is in E, that is AB inverse is belongs to this set. That means H is a subgroup of G, right? That's the idea. Okay. So that you keep in mind. Yeah. So let's look at one more problem in this kind. So let's take let G be a abelian group as before. G be an abelian group. In this case, we are collecting all square elements of X G. So what we are telling is it is a subgroup of G. Okay, so what is an example? If you take a group like H is equal to take G is equal to Z 4. So what is this set? 0 1 2 3. Okay. So now what we are collecting, our H in this case are the X squares. So 0 square, 1 square, 2 square, 3 square, all are modulo addition modulo 4. So we need this. So this is 0 plus 0, that is 0 itself. 1 plus 1, right, it is 2 under modulo 4. 2 plus 2 is 4. 4 is 0 modulo 4. 3 plus 3 is 6, that is also it's 2 modulo 4. So this becomes 0 2. Now you can see that this is a subgroup of Z4, because if you add 2 plus 2, it is 4, again 0. If you add one more time 2 plus 2 plus 2 6, then you get 2. So this is a subgroup of G. So generally we need to prove that. So what do you want to do? So let's prove this is a group, all square elements of G in an abelian group, right? So let's take the idea AB in H. What we need to prove is so we have AB in H means what? That means A is equal to some G square, right, for some G in G. Similarly, B is equal to some H square for some H in G, right? That's the idea. So A equal to G square and B equal to H square. Okay. That's why, because A and B are square elements of so it has to be equal to some squares. What we need to prove is AB inverse is in H. That is, we need to prove that AB inverse equal to some K square for some K in G. We need to prove it. Need to prove. Okay. So how do we do that? Right. So what you want to do is we multiply AB inverse. So if we multiply AB inverse, A is given, it is G square, B is H square, so H square inverse. So now this can be interchangeable, right? So we can write G square and it can be written as H inverse square. So this is equal to G square, or you can write it as G times G, H inverse times H inverse. Okay. Now by it is an abelian group, so you can interchange this. I mean, you can make it commutative property. So it is equal to H inverse G H inverse. So now this is nothing but G H inverse whole square, right? Now note that G is in G, H inverse is also in G. Being G is a group, GH inverse in G. So let's call it is some K. So what is this is nothing but K square, where K is in G. So what we have proved, AB inverse equal to K square for K is in G. That means AB inverse is in fact in H. So that means it is a subgroup. Okay. Now let's look at one more thing. It's a very popular one. What we call it is a center of a group. So center of a group. Okay. So what do you mean by center of a group? So center of a group is simply, we denote it is by Z of G. G is a group, then Z of G is a collection of all elements in G where X commutes with everybody in G. Okay. So you should write like that. For all Y in G. So if you write in words, this means all those elements in G which are commutes with all elements in G. Okay, one those element is E, because we know that EA is equal to A is equal to AE. So that means EA equal to AE. So that E commutes with everybody. So okay, E commutes with everybody, right? So is there any other elements is there, we collect it. So that is what we call the center of G. So all elements with commutes with everybody. So one fellow, so set of G is a non-empty set. It is not equal to empty. Why? Because E is always an element of set of G. Okay. Now what we are going to prove is, our claim is Z of G is a subgroup of G. Okay. So how do you prove that it is true? So let's take two elements from Z of G. So let's take AB in Z of G, right? So that means what? Ax equal to xa for all x in G. Similarly, bx equal to xb for all x in G. So they commutes with everybody, right? Now what we want to prove is, we need to prove that AB inverse in Z of G. So what is the meaning? That is, AB inverse commutes with everybody, or AB inverse x equal to x into AB inverse, right? So let's take a general element. Let x belongs to G be a general element. It can be anybody. That's the meaning. So we start with AB inverse multiplied by x. This means we can make it like this: AB inverse x using associativity. It is true. Now A commutes with everybody means A commutes with, see, A commutes with everybody. That's what we have taken. So A commutes with the element B inverse x. So I can write it is B inverse x of A, because A commutes with everybody. Now I will recall the Sox-Shoe property of elements. Like, you know that xy in a group, xy all inverse is equal to y inverse x inverse. In that fashion, I can rewrite this B inverse x like this. It is, you can write it x inverse B all inverse times A. Why? Because if you open it, so x inverse B all inverse, if you open it, it should be in the otherwise, right? So B inverse x inverse all inverse, that is B inverse x. So that's why I have done. I have just changed it. So you can note it here, right? Okay. So we can write it. Now why I did write that? Because B is a element of Z of G. See, B is an element of Z of G. So I can play with it. So I can B commutes with everybody. So B commutes with x inverse. So I can write Bx inverse all inverse times A. Now apply Shoe-Sox property. So that is, you have oppositely it will come x inverse all inverse B inverse times A. So now it is what? X B inverse A. Now again, okay, yeah. Now again A commutes with this fellow, so you can write it as A x B inverse. Now A commutes with everybody, so A commutes with x also. So that it is equal to x AB inverse. So what you proved is AB inverse x equal to x AB inverse. That means AB inverse commutes with everybody. That is, AB inverse is in Z of G. So we are done. So in that fashion we can prove that Z of G is a subgroup. So this is for any group. So any group you collect all elements which commutes with every element of G, this becomes a group. Finally we look at one more in this fashion, then we'll wind up this. So this is what we call the commutator of. So before we have looked at every element commutes with everybody, here we are looking at only those fellow commutes with a single element. So commutator of A depends on A. It is all elements in G such that it commutes with element A. So all elements commutes with A. All elements commutes with A. So A is an element of G. So we prove that the commutator is a subgroup of G. So we call it is a commutator subgroup of subgroup of A in G. Okay, how do you prove that? The same method. So we take two elements from this. So let's take two fellows, H and K, from C of A. So what you get is HA equal to AH. Similarly, KA equal to AK because it commutes with A. First, what we want to prove is if H and K commutes with my claim is if H commutes with A, H and K commutes with A inverse, right? So let's see that, but how that happens. So suppose you take HA equal to AH, then try to multiply both sides by A inverse. So that means HA A inverse equal to AH A inverse. This means HE equal to AH A inverse, that is H equal to AH A inverse. Now what you want to do is, so here what you have done, you multiply A inverse. Okay, you should write this. So multiply A inverse in RHS, right side of the equation. So that's what happened, right? Now what you have to do is you have to multiply A inverse in left side. So if you multiply left side, what happens is A inverse H is equal to A inverse A H A inverse. So this is E H A inverse, that is equal to H A inverse. So what you have proved is A inverse H is equal to H A inverse, that is H commutes with the A inverse, right? So that keep in mind. So A inverse H is in fact equal to H inverse. Okay, so we will use to prove the idea. So what we need to prove is, we need to prove to prove it is H is a subgroup, we need to prove HK inverse in commutator of A, right? So how do you prove that? So we take HK inverse multiply with A, we need to prove that A into HK inverse, right? So what you have to do is yeah, you have to write like this, then you can apply Shoes-Socks property. So if you apply Shoes-Socks property, you can write this. It is yeah, A inverse K whole inverse. So if you come in other way, you get that we have done just before that. So this is true. Now we have proved that if H and K commutes with A, it commutes with A inverse. So K commutes with A inverse. So I can write this is like that, right? It is because K commutes with A inverse. We just proved it. Now apply Shoes property, revert it back. What you get is A K inverse, right? Now H commutes with A, so you can make it AH. So what you have proved is HK inverse is in fact equal to A HK inverse. So that means HK inverse commutes with A, or HK inverse belongs to commutator of A. So that means commutator of A is a subgroup of G. Okay, so this is a one-line subgroup test which is very useful to prove anything like that. So finally we do one more thing which will be useful in our next lecture. So so it is last but not least. Okay, so we take let G be a group and A is an element of G. Then we denote a particular a subset H like this, and the notation is A power n, where n belongs to Z. We take all the integer powers of n. So this means everything will be there: A power 0, A power 1, A power minus 1, A power 2, A power minus 2, like that is going. So complete thing. So this is so we prove that this is in fact a subgroup of G. So let's prove it very fast. So let's take two elements again, H and K, from this subgroup. So what is the look of this? So H will be look like some A raised to n, K will be look like some A raised to m. Now if you multiply HK inverse, what happens is A power n, A power m raised to minus 1. So this is we have already looked at. So it is A raised to n, A raised to minus m. So this is A power n minus m. This is belongs to A because for n number integers, n minus m also an element of integers. So this A power n minus m is actually an element of. So this is a subgroup of A. So this subgroup, we can see that every element is expressed in this subgroup. We can say every element of is expressed as the powers of A. So we call it is subgroup generated by A. Okay, subgroup generated by A, or similar, because it is cyclic rotation of A, we call it is also cyclic group generated by A. Okay, or cyclic subgroup in this case. We can make it a subgroup generated by A in the group G. Okay, so this is a motivation to define what is actually mean by cyclic groups. So we will be seeing that in the next lecture.